Hello again. So in this video, I'm going to discuss the homework that follows the introduction of limits. And when we're working with limits, there are 3 or 4, 5, and by the end of this class, we'll learn like 5 distinct approach. But there are, as of right now, 3 or 4 distinct ways to handle limits, and you have to know, if not all of them, but at least pick a favorite and be good at that one. The first approach is graphing approach, and I encourage you to watch all these lectures. They are pretty short, but they give you everything you need to know to understand the graphing approach, and graphing approach is one of the most powerful approaches. Guess why? Because you are allowed to use calculators in this class to graph functions. So if you understand the graphing approach, then simply you have to use the calculator and graph the function, and then you know what the limit of that function is, if it exists, and you'll be able to see that it doesn't exist when it doesn't exist. And again, please watch all of these lectures before continuing into the homework. Throughout this video and in the future, I will be referring to this as if you have watched it all. So that will save us some time, and it will guarantee an effective and efficient communication. So let's jump right into the homework. And the homework is about finding the limit using the graphing approach. So the idea is very simple. You see the limit of a function, you look at the graph of the function, and then you answer the question. So the limit of the function as x approaches to 3 is equal to -4, clearly. And how do we know that? We know that because we watched this lecture, and we know what a two-sided finite limit looks like. So the visual representation of this two-sided limit is something like this. So the function itself doesn't have to exist at this point, but as long as both ends of the function exist on both sides of this point, we say the limit does exist, and it's equal to the output or supposed output of the function at that point if there was no discontinuity there. So the answer to this question is the -4. And let's continue. X approaches to -3, same here. The answer is 4. And again, this homework set may not be the most representative homework set to test your understanding of the limits, but it is what we have, and you shouldn't have any problems with any of these problems. So as x approaches to -3, you see how the function is continuous here, so the answer is just 2. At -3, again, this is the behavior that we're looking at, so the answer is -6. It's not about what the function is at that point, it's about how the function behaves around that point, and that function approaches to -6. And yeah, more problems. Left-sided, right-sided, two-sided limits. So again, where do we learn all of this? We learn it from over here. This is the right-sided limit. Here's all of them. Again, it just makes sense to watch all these lectures first, right? So to understand what's going on. So I'm just going to be answering this question. So the limit of the function as x approaches to -4 from the left is -1. As you approach from the right, it's +1, and two-sided limit does not exist because these two do not coincide. Very easy. Another one, so this time we're looking at the function at 2. At 2, the function is continuous, so when the function is continuous, all 3 limits coincide, and vice versa. So the answer is 4, 4, and 4. At 0, 0 plus, 0 minus, the answer is -6. That's the power of the graphing approach. You have the graph, you know what the answer is. If you allowed to use technology to produce a graph, then this opens such a huge door of opportunity for you to just not worry about limits at all. And we will be needing the limits in calculus too, big time. So at 2 from the left, it's -2. From the right, it's also -2. So the two-sided limit also exists, but they just don't ask about the two-sided limit. At 2, again, we see that two-sided limit does not exist, right? Because these two ends don't coincide, they don't connect. But the right limit exists, the right-sided limit exists, and the left-sided limit also exists. This one approaches to -5, this one approaches to 3. I don't even get to graph anything here, but I will in the future. So 4 at 4 on the left, it's -5. On the right, it is 1. In the middle, two-sided limit, it does not exist. Another 4 on the left, it's 3. On the right, it's -3. And they don't ask for a two-sided limit. There are a lot of problems, huh? At 2, both are 0. Two-sided limit also exists and it's equal to 0, but they just don't ask for it. Alright, we got 3 out of 7 already. Let's move on. Alright, so this is when they don't give you the graph, and this is when Desmos comes in. I'm going to graph it myself. And looking at this graph, I can tell you that at -7, where is -7? At -7 on the left, function goes up to infinity. So plus infinity. On the right, it also goes to infinity. And therefore, two-sided limit. And here, when both sides are infinity, sometimes we do say it's infinity, but sometimes it's also okay to say it doesn't exist either way, because infinity technically is not a number. So let's see. Oh, they're also asking us about the vertical asymptote. The vertical asymptote is at -7. So let's see if they like our answer for part C, and they did, so we're good. So again, notice how we use Desmos. The graph wasn't given, but with Desmos, all graphs are given. At -6, we have infinity. On the right side, we have -infinity. Two-sided limit does not exist, and that's it. It's that easy. Here, not given, so we graph it ourselves. And it says increase the function f of x increases without bound as the value x approaches to 1. Okay. So how do we write this symbolically? Okay, got it. So that means the limit of the function as x approaches to 1. So since they don't specify the side, it's a two-sided limit. And since the limit is infinity, we say exactly that. Really love this problem. Same here, different function. What's going on at -2? This is just so we can see what's going on. Where is that 2? Oh, it's an asymptote. And on the left side, we have -infinity. On the right side, we have positive infinity. And the two-sided limit doesn't exist. So the asymptote is x is equal to -2. Do you see how things are much, much easier when you're allowed to graph? Same thing, right? So here, let's just visualize it. I think I know what the graph looks like, right? Based on their description of what's going on at -2, but doesn't work to graph it. and so as x approaches to -2, the function, which is, let me be smart ass over here and try to put f of x here. Will they accept that? I don't know. Let's see. It goes to -infinity. Oh, very nice of Newton. Wow, thank you. I'll take that. And now the punishment. -6 on the left is -infinity. Another -infinity, and therefore the two-sided limit is also -infinity. And we got 4 out of 7 objectives already, and it's only been, I don't know, I lost track of time. +3, 5. Let's remove this. So something going on at -3, right? I guess we do have an asymptote. We can actually play with the graph here, and we can answer the questions now. On the left side, it's -infinity. On the right side, it's +infinity. In the middle, it doesn't exist. And vertical asymptote, just because the limits are plus or minus infinity, we do have a vertical asymptote. That's just a fact. And I don't need to type x here. Now, if you read the solution, it may look more complicated than what you really need. Same here. And as we're doing this, you may start recognizing some patterns. And this is how you strengthen your analytical skills. In this case, on the left we have infinity, on the right we have infinity, and two-sided limit is also infinity, and therefore the limit is, the asymptote is at x equals -8. We did 5 out of 7 objectives. Graphing approach rocks. Oof. Let's see. The red vertical dash line is a vertical asymptote. You may pan and zoom in. Oh, okay, looks good. Looks like Desmos. You may also click on the point to find its coordinates. As x approaches to infinity, what is the output approaches? That's such a good exercise. You can see that as x approaches to infinity, so on the far right side, the function drops, but it doesn't drop like exponential function would have dropped. So it approaches to, you can see here on the left side, to -1. And how do we know that? Again, because we watched this lecture right here, one-sided infinite limits, and we recognize behavior, not this lecture, but this lecture. We recognize behavior like this from the lecture, right? And that's how we know what the answer is. All right, this one is x approaches to -infinity, so we're going to be looking on the left side, and it looks like the graph approaches to -3. Such a good exercise. Oh, yeah. For this one, if you weren't allowed to graph this by hand or with technology, you would have to either figure out the limits analytically, or in any other way. But in our case, we're using the graphing approach, so we're just going to do that. We're going to graph the function. Only if I could figure out how to type -4. So this is what the graph looks like. It looks like the ones that were shown in the previous problems. And now we need to start figuring out the limit as x goes to infinity and -infinity. So first of all, we do see there is a horizontal asymptote, right? And if we keep zooming on the right side, we see that it approaches to -1/2. Now, if we start zooming on the left side, let's see. We see that it approaches to -0.6. So the left and right limits don't have to coincide. Now, if you have to prove this analytically, it's the matter of looking at the right coefficients. So as x approaches to the right, this term, let me just rearrange this. As x approaches to infinity, this term goes to 0, and this term goes to 0. So the answer will be -1/2. However, when x goes to negative infinity, this term, in comparison to this term, will be insignificant. And then the answer will be -3/5. So that's the analytical approach, but nobody's asking you to use analytical approach here, as we are practicing the graphing approach. Another one. So this is the arctan of 3x plus 9x squared. Oh, where's the graph? Ooh, what a beautiful graph. And so as x goes to infinity, this is pretty much becomes the well, it's 1.571. 1.571. What does 1.571 remind you of? It should remind you of something. It's half of pi. So pretty much as x goes to infinity here, your limit is the output of the tangent inverse for large values of x, which we know is pi over 2. And on the negative side, it will be negative pi over 2. Why would it be negative pi over 2? I don't know, because when you square the infinity, on the left side, pretty much the limit is the same as on the right side, so there shouldn't be negative over here. If you look at the graph, clearly you can see that there's some sort of symmetry, not around 0. It's not quite symmetric, but in terms of the end behavior, it does show the symmetry, so it's pi over 2. All right, so maybe a couple more problems here. What's the question? Find the limit as x approaches to infinity. Looks like -1, right? Unless they're trying to be tricky and it's like some fraction of that is close to -1, but no, they're not trying to be tricky. It is what it is. Another one. As x approaches to infinity, the answer is 3. Look at it. It screams the limit is 3. Couple like some ugly function. So either you figure this out analytically, which you can if you have the skill and the time, but we're practicing the graphing approach, so we're just going to look at the graph. And according to the graph, as x goes to infinity, it approaches, looks like -1/2, but not quite. So it could be that it is some logarithm of something that is close to -1/2. So we may have to use some analytical skills here. And the first thing we want to do here is we want to simplify this and use the property of the log. And instead of difference of logs, write difference of log of the quotient. So this is what it's equivalent to. And now, so instead of looking at this function, I suggest us looking at this function. So let's take a look at this function. This function is a different function again, but the limit of this function, because it's just a rational function, the limit of this function is 0.62 as x goes to infinity. What is the limit of this function? Do you recognize this? Well, it's just the ratio of the leading coefficients. And therefore, the limit of the original function as x approaches to infinity is the ln of this. As you can tell, this is the number that is close to negative 0.5, but not quite negative 0.5. So the correct answer is ln of 5/8. So this is where you have to have like, I mean, some understanding of what's going on, and analytical skill is still necessary sometimes. It would be nice if we could just avoid it completely, but that's not the case. All right, so this one looks crazy around 0, but the question is not what it is around 0. The question is what it does at infinity, and it looks like at infinity on the right side it goes to negative infinity, and on the left side it goes to positive infinity. So this is the answer. And how do we know that? That's because we watched this video right over here. Is it this one? Yeah, right here. Right, so again, please watch those videos if you haven't yet. And how many more? I'm getting tired. And another function, negative 4x squared plus 2x plus 4 sine 9x to the power 5. That's pretty crazy function. Ooh. It's beautiful here. What's going on here? Hold on. Oh my god, look at this. Look at this function. How pretty it is. But as, again, the overall pattern is what? It goes to negative infinity as x approaches to infinity and negative infinity. So both answers are negative infinities here. Maybe one more? Oh no, we are done with graphing approach. If you have any questions about graphing approach, please reach out.